All right. So, yeah, as Eike just said, we will revise a couple of basic statistical concepts. And there's a good reason for that, because uncertainty, yeah, played a very important role in good old-fashioned statistic for a very long time. Yeah, the difference in statistics is perhaps that they haven't used these two terms, aleatoric uncertainty and epistemic uncertainty, that often. Yeah? So they spoke about uncertainty, but they never have really distinguished between these two types of uncertainty. And if you look at this picture here, it's very similar to what Eike presented in the beginning with the medical images. Yeah, so we have on the left-hand side the data where the aleatoric uncertainty is coming from, actually, yeah, from a generating process. On the right-hand side, where the prediction, or in statistical terms, the statistical inference takes place. This is where the epistemic uncertainty is taking place. Yeah, so where we make statements on or about the generating process. And these modern machine learning approaches, which are considering different types of uncertainties, the distinguishment between the two, they are based, mostly based on statistical concepts and even further develop many of these concepts. Yeah, so that's why it's really important to have a solid knowledge about all these statistical concepts in order to understand what the modern machine learning approaches are doing. This is why we will revise this here very quickly. Okay, so we had a couple of buzzwords on the first slide. Statistical inference. So what is inference about? It's about making statements or hypotheses about some parameter, some process we are interested in, future outcomes, etc. And the statistical inference now adds just the uncertainty component to it, yeah? More precisely, an uncertainty measure to these statements. Yeah? And the question is, well, how do we measure uncertainty in a reasonable way? And the statistical answer for this is we use a probability. Yeah? So a probability is our measure for uncertainty. Let's have a look at a quite vague definition of probability. Yeah? So how we can define it, yeah? Roughly speaking, as a heuristic, more or less. Yeah? The following could be used. So we consider some event A, which might represent our statement or hypothesis, whatever we are interested in. And then the probability of A simply measures the uncertainty about the outcome of A. Yeah? Just a vague definition. And because it's quite vague, you might ask, well, how do we interpret uncertainty here in this vague definition? And in statistics, there are more or less two schools of thoughts which are answering this question in a different way. The one is the interpretation based on limiting relative frequencies, which is giving rise to the frequentist inference. And the other is based on the degree of belief interpretation, which is giving rise to Bayesian inference. Yeah, so we will distinguish the two in a minute and prove out this part. But first of all, we want to consider what both schools have in common. Namely, they have both in common the statistical modeling. Yeah? And the statistical modeling includes some relevant components. The first, the most important component perhaps is the data. Yeah? So the data set D, because this is our source, which we use to create a statement, to come up with a statement or a hypothesis which we want to check. We want to predict something about the data. We want to find out relationship in the data. Yeah? I think I don't have to tell you here how important data is. And the next important component in statistical modeling is the statistical model. Yeah? this is at the heart of the modeling. And we will denote this simply by calligraphic P. It's a family of functions P theta with a parameter space capitalized theta. Yeah? And all these functions are parameterized by these thetas inside the space. These P thetas are in most cases referring to probability distributions. Yeah? That's why it's sensible to use here the notation P theta. But it can also be something not specifically a probability distribution, but also a regression function, a probability density function, cumulative distribution function, whatever. Yeah? So depends on the context. But in most cases, yeah, so in the very classical statistic approach, it's a probability distribution function. That's why we will consider here this is the as our example throughout this part. Okay, and regarding the parameter space, we can make a distinguishment between specific cases. So there is the case of a parametric parameter space where simply this theta is finite dimensional. Now, for instance, if the statistical model corresponds to all Gaussian distributions which we can think of. Yeah, so you see here the correspondence P theta is simply the Gaussian distribution or normal distribution here with parameters mu and sigma. Yeah, so the expected value and the variance or the standard deviation in sigma. And both of these parameters are coming from a parameter space, which is in this case the real line times the positive real line. Yeah, so this would be our theta. Finite dimensional has dimension 2, obviously. And as I said, here we could also think of something which is not necessarily a probability distribution, like all regression, linear regression hyperplanes we can think of, and then the parameter space would be all possible weight vectors we have there. Then on the other extreme, yeah, regarding the parameter space, we have the case of a non-parametric parameter space theta. This is the case where it is infinite dimensional. For instance, when our statistical model consists of all probability distributions with zero mean, for instance. Yeah, so obviously we can not find finite dimensional theta, which is parameterizing this set here appropriately. Then it can also be reasonable to have a mixture of the two. Then we are in a semi-parametric case. Yeah, then the theta, the parameter space has a finite dimensional component and an infinite dimensional component. Yeah, an example would be here the Cox regression model, which is typically used in survival analysis. There, the hazard rate function is an infinite dimensional component. It's a function, and the effect parameter is typically a finite dimensional parameter. Yeah, some weight, more or less. Okay, and the statistical inference process is then as follows. Yeah, so we have this usual flow, more or less, in statistical inference. Yeah, so we have the data as before, yeah, so the DNs. And we assume in the classical setting of statistics that these data points, the ZIs, they are IID. And there we can again distinguish two cases. And the very classical setting is where we simply have that these ZIs do not come with covariates, or in machine learning jargon, the features. Yeah, the ZIs correspond to the YIs. So in machine learning, you know that then this is relating to a label. And we assume that these YIs are distributed in an IID, in an identical independent manner according to some probability distribution P theta, yeah, in our statistical model. And this is actually then where the aleatoric uncertainty comes from in the statistical process. Yeah, so this data is generated via these distributions. So this is an uncertainty we cannot get rid of. The other case is more typical for a machine learning setting, which has also been considered in statistics, of course. Yeah? So in statistics, it's then called covariates, where we have features. So our data points are pairs of X and Y's, yeah, of features and labels, in statistical terms, covariates and outcomes. And we assume then that the yi's are distributed in an IID manner according to p theta, which is then a conditional distribution conditioned on the corresponding xi for the yi. Okay, and then the process goes on. So this is the more or less assumption, the statistical assumption, how we model this. And what we want to do with statistical inference is we want to infer this theta, which is giving rise to the data, or even more perhaps infer the entire p theta, yeah, the entire distribution. And then we can continue, yeah, after we have inference about the theta or the p theta, we can do prediction, for instance. Yeah, we can use the parameter or the corresponding probability with this parameter to make prediction of future outcomes or whatever, or do hypothesis testing, for instance. Okay, so this was a quick refresher on statistical concepts in general, and now we will distinguish between the two cases, these two schools of thoughts and statistics, the frequentist inference and the Bayesian. Let's start with the frequentist inference. So we recall our very vague definition of probability. Yeah? Simply the probability of A measures uncertainty about the outcome of the event A. And the frequentist statistician is now refining this vague definition in the following sense. Yeah? So the probability of an event A, denoted PA here on the left-hand side, this is the fraction of times we would see A when we would repeat the situation of this event infinitely often. Yeah? And intuitively, this makes sense if we once again consider the coin flipping scenario, and our event we are interested in is perhaps the event that the coin lands heads. Yeah? If we have a fair coin, we flip it many times. Yeah? So here 500 times, and track how many times the coin has landed heads. You will see, okay, the fraction over the time is converging to the fair probability, or the probability which is corresponding to a fair coin, namely 1/2. You can do the same for an unfair coin, yeah, where this coin is biased, yeah, so it is only showing 25% of the time the heads, yeah. Then we do the same, track the number of times this is happening, and we will see a similar picture. And the underlying idea is, or the philosophy more or less of the frequentist is that probabilities are nothing else than objective properties of the occurrences in the real world. Yeah? So there is simply a probability which can be explicitly specified, but we don't know it. Yeah? We can only find out when we would repeat the random experiment or the situation over and over again, and track how many times this event we are interested in is happening. Of course, this has for practical applications the drawback, yeah, that we obviously cannot repeat some events over and over again, and we don't want to repeat them over and over again. Yeah, so perhaps when we want to predict the probability that an earthquake will happen, yeah, this is something we definitely don't want to repeat over and over again. But still, when we do frequentist inference, yeah, the idea would be the probability of this event is something indicating how much it would happen when the situation would be repeated on and on. Okay, so in frequentist inference, how is the inference actually done? Yeah, so what is the workhorse there? And more or less the main layer in the frequentist statistics is a point estimate of the theta of the parameter we want to estimate. Yeah. So this estimate is kind of a best guess. Yeah. Something we want to use for a proxy of the theta we are interested in. And how is it usually done? Well, we specify a function of the data. Yeah? So we plug in the data inside the function, yeah, which is kind of extracting exactly the properties which are characteristic for the theta kind of. Yeah? And of course, because the data is limited, yeah, there is uncertainty involved. Yeah? So we do an approximation error, and we are not ending up with the true theta in the in the usual case. Okay. What are typical approaches to come up with a function g? Yeah. So the most common approach, perhaps from statistics, also relevant in machine learning, is via maximum likelihood estimation. Yeah. So we have this IID assumption, and then we build the likelihood of the data. Yeah, so we are plugging in the data inside the statistical models we have, the p thetas. Under the independence assumption, this is corresponding then to a probability over the statistical models for the corresponding data points. And then we look for the theta, which has the largest likelihood to have generated the data. Yeah? And this entire thing, this is our function g. Yeah? So you see here, the data comes in, the zi's are the data, and this entire thing here, this is the function g. Yeah? Just to have a concrete example. There are also other methods available, yeah? Just to name a few: method of moments, plug-in estimates. Now, plug-in estimates is perhaps a generalization of the method of moments. There are also more generalizations of the maximum likelihood estimate we see here, yeah, for machine learning purposes. Empirical risk minimization is something which generalizes the maximum likelihood approach, where we have a loss function, yeah, which we sum over, where we plug in the data, sum over it, and then minimize with respect to the parameters we have. This is actually something which we also do in maximum likelihood estimation if we would simply use minus the loss function. Yeah? So then we would not maximize, but rather minimize. And in statistics, there is this term of M estimation, which is essentially the same as this empirical risk minimization, where we have a criterion function and proceed in a similar way as in empirical risk minimization. Only the notations are, yeah, so the terms are different. Yeah? So here we speak of a loss function in empirical risk minimization, and in M estimation, we talk about a criterion function. Yeah, but the principle is the same. Then there's another generalization even of empirical risk minimization, or M estimation. It's the Z estimation, where we have a criterion function which we want to for which we want to find the root. Yeah, and if you have a criterion function or a loss function which we want to optimize, yeah, we know under specific assumptions on the loss function, yeah, the optimum can be found if we look for the zero of the gradient, yeah, in specific sense. And so a natural criterion function for Z estimation would be simply a gradient there. Yeah? But there are also other ways to do this. I don't want to go into details. So it's kind of a generalization of the others above. Okay, now, so these are some approaches also coming up in machine learning, as we can see. And once we have these estimates, yeah, the point estimate, either from maximum likelihood estimation, empirical risk minimization, whatever, we are interested in the properties of these estimates. Yeah, so how good is the approximation? How far away are we from the thing we want to estimate? Also the quality actually, which is telling us perhaps also even a bit more about the properties of this estimate. And there are a couple of measures to specify the quality of a specific estimate, and arguably the most common one is the mean squared error. Also quite well known in machine learning, I think. But nevertheless, let's recall, so the mean squared error of an estimate, what is it? It's simply the expected L2 deviation of the estimate from the term it should estimate, so the theta in this case. And the nice thing about this mean squared error is it admits a bias variance decomposition. So we can decompose it into two terms. A bias term, which is telling us something about how far off we are in expectation with the estimate from the theta, and the variance, which indicates how much fluctuation we have in the estimate. So how also kind of measuring uncertainty in this theta hat in some sense. And this mean squared error is important for machine learning purposes as well. So in machine learning purposes, we are rather interested in predictive uncertainty, where we don't make inference kind of the theta. We go a step further. We use this theta hat in a predictive model. So perhaps plugging into it into a linear regression model, and the theta hat is our weight vector. And then we can also ask for, well, what's the mean squared error of the prediction for the ground truth prediction? And we can do a similar decomposition. Only the difference is that we get an additional noise term, which is not showing up when we make here inference about the parameter. This is due to the prediction nature we have there. And this decomposition of the predictive uncertainty is also relevant from an uncertainty perspective. So this generalization error measured in mean squared error. This is the predictive uncertainty, can be considered as the predictive uncertainty, and the bias variance as the model uncertainty, and the noise, the data uncertainty. Finally, it's worth mentioning that the mean squared error is kind of a prime example, but of course there are many different other measures to assess the quality of an estimate. So perhaps depending on the context, the mean squared error is not defined at all. It depends on the parameter space. So here we make use that we have here the possibility to define an L2 norm, which is not always the case for every parameter space. So there are also other measures available. Also regarding the focus of the quality, it might be also sensible to look at the mean absolute error or the KL divergence, for example. Okay, and one thing I also wanted to mention is the estimation via proper scores. So how can we come up with an estimate for the p theta directly? So now we are not interested in the theta, but in the entire p theta, which is something also relevant in machine learning, quite obviously. So to find out what the data generating distribution is. And in statistics, this has been also considered for a while. And the approach suggested there is via, and the frequentist statistic, to be more precise, is to tackle this via so-called proper scores. Okay. In order to understand that, let's assume that the y's are coming from a domain calligraphic y. And then a score is simply a function with the signature, with probability distribution. So we are now in the case that the statistical model corresponds to probability distributions, and we assume that the ground truth is included there. It is a mapping from the statistical model and the domain of our data to the real valued numbers. So this is quite not restrictive, right? So every function which has this signature is a score. So we need to specify what are good scores, what are bad scores. And for this, we have different properties. And one property is the so-called proper property, which is essentially saying, well, if we look at the expected score of an estimate p hat for our p, of this p theta, think of this p as the p theta. The expected score of our estimate p hat, which we will denote in a more convenient term by bold as p hat p. This is always at least as large as the expected score we would have if we would plug in for the estimate p hat the ground truth p. And this holds for any combination of p hat, any combination of estimate and ground truth. So this gives an incentive that the score can be minimized in the first component only if we use for the estimate the p, the ground truth p. We can only make it more stricter, which is giving rise then to the strictly proper property, where we have a strict inequality here for these expected scores. Every time the estimate is not corresponding to the p. So we give a incentive in order to predict with the p hat the p. So we have a unique minimum there at the ground truth in the first argument. In order to illustrate it even further, we can also rewrite this strictly property in the following convenient way to see it even more clearly. The minimizer of the first component, of the estimate component in this expected score, is achieved when the ground truth is p, only if we use here the p as the estimate. Okay, and then what can we do? Once we have such a strictly proper score function, we can do kind of empirical risk minimization. And this is also done in statistics and later on also in machine learning. So we simply use for the guess p hat for the p, the one which is minimizing the first component if we would plug in here for the second component our observations, namely the yi's, right? And yeah, you might ask, well, what are specific examples of such score functions? And in machine learning, actually, we use score functions all of the time. So consider the case where the domain y is discrete. There, the cross entropy is a function which is a strictly proper scoring function. So all the neural networks minimizing cross entropy are doing kind of, when we look at this, the right thing. Worth mentioning also the Breyer score, also often used, or in the continuous case, so the logarithmic score related to the maximum likelihood estimation, or the quadratic score in statistics, or also mean squared error is it more or less what we do there when we use the quadratic score. So we have sketched this here for the case where we don't have features or covariates. Of course, this can be also extended to the case where we have features and covariates. Obviously, if this is used in machine learning, then also covariates and features can be used as well. And the interesting thing about these proper scores is that quite recently there has been a work which has shown a quite general decomposition in a bias and variance term as we saw for the mean squared error. So you also have this structure bias plus variance plus noise. This is shown here in this recent AI stats paper. Okay, so well, we have now considered the quality measures of the point estimate to kind of get some more information. Another typical way in the frequentist statistical inference is to define confidence regions, yeah, which are kind of also representing uncertainty in a specific way. We'll talk about this in a second. So first of all, let's recall what confidence intervals are. So we start with the simple case. Our parameter space is a subset of the real line. Yeah, so the theta is simply a real number. And then the confidence interval is nothing else than an interval where the boundaries of the interval are functions of the data. Yeah? So here the lower boundary A is a function of the data. The upper boundary B is also a function of the data. And we call this data-dependent bound we have here 1 minus alpha confidence interval when the following holds, namely the probability that the theta we want to estimate is inside this confidence interval. This probability is at least 1 minus alpha. And this holds for every theta in our parameter space. Yeah? And important to note here is, once again, the confidence interval is random. Why? Because the data we get is random, right? So the data is generated by some probability distribution, so nothing else than random observations. And if we plug in random observation into a function, we still get something random, right? And this holds true also for these boundary functions A and B. But although the confidence interval is random, the theta is fixed because we are here now in a frequentist statistical inference case, all right? So once again, the probabilities are objective properties of the real world. So is the theta. We just don't know it. And to illustrate this, yeah, so even further what is meant, and also to make the connection to this frequentist definition of a probability, this is quite good, always with the confidence interval, is the following picture. So let's assume our ground truth distribution P theta is this orange density here. The theta here is perhaps the expected value. And then let's assume we could draw every time new samples from this probability distribution. Yeah? So these 5 points, this is our data. And now we use this data, yeah, map it to some point estimate. And around this point estimate, we can perhaps specify some offsets, yeah, to the left, to the right. These are then the functions A and B. Yeah, and we get a confidence interval around that. And when we do this repeatedly often, yeah, we sample from this distribution a data set, use our functions to create the confidence intervals. What will happen? These confidence intervals will cover the theta 1 minus alpha times. Yeah, this is perfectly in line how the frequentists are interpreting the probability. Yeah, so we would repeatedly often do this random experiment, yeah, and get the desired probability of at least 1 minus alpha. All right, so for confidence intervals, it's also possible to have different prefixes, yeah, when the properties are perhaps a bit more relaxed or even more stronger. So one is an asymptotic confidence interval. It's relaxed in the sense that this coverage here of 1 minus alpha thus only holds in the limit, yeah, if you would see infinite many data points. A more stronger assumption would be the uniform confidence interval, where we have the infimum here over the theta, and the coverage is does hold, and we can also combine the two, yeah, so we can also have asymptotic uniform confidence intervals. Then we talked here, yeah, for illustration purposes about the simple case of a parameter space which is a subset of the real line. Of course, the parameter space can also be more complicated, as we saw before. For instance, it could be a parametric but multivariate parameter, so a theta in the RD. Then we can also do a similar definition of a confidence interval. Yeah, so we have to just to extend it to the multivariate case, and then we talk about a confidence region, yeah, instead of an interval. And this region can refer to different objects like a hypercube, an ellipsoid, or whatever. In the non-parametric case, yeah, so where we usually have that the p theta we are interested in, yeah, so the statistical model is a entire distribution from yeah, not finite dimensional parameter space. Yeah, there we often use the notation of a confidence band. Yeah, so like a tube around the p theta for all possible outcomes. Yeah, for instance, for the density function. All right. Let's have a look at a way how to construct confidence intervals or regions. Yeah. So what are typical ways to do this? One way is to make use of concentration inequalities. This is possible when our parameter estimate theta hat is of a specific type, a U or V statistic. Then we have concentration inequalities available, stating how much the point estimate deviates from its expected value. When it's an unbiased estimate, expected value is the theta it should estimate. Yeah, and then we can rearrange this concentration inequality to get the desired coverage. Another variant, quite obvious, yeah, would be to have an exact variant where we simply would use the sampling distribution, so the distribution of the theta hat. Now, the theta hat has a distribution. It's, once again, a function of the data, so it's random. A random variable has a distribution, and when we talk about the distribution of the theta hat, we are referring to the sampling distribution. And this sampling distribution could also be, of course, used somehow to get a specific interval or region where we can say, yeah, with at least this probability, the theta we want to estimate is included. Problem is, of course, well, the sampling distribution might be quite complicated, difficult to access, and what we do then is we use approximation methods. One typical approximation method is via bootstrapping, where we do resampling of the data over and over again and try to find out how the sampling distribution looks like. Yeah. Once again, estimating the distribution, so we get there an additional estimation error. Additional source of uncertainty. Another quite common statistical approach is to have an asymptotic variance, yeah, where we resort to the asymptotic distribution of the sampling distribution. And this is typically done by means of a central limit theorem, or in other words, showing that the estimate is asymptotically normal distributed. Yeah? So here, again, quite vaguely, depends on the context, of course, where the point estimate is coming from, parameter space, etc. We have some specific assumptions, and then we can show if we standardize the estimate. Yeah, so here, subtract the theta and then divide by the standard deviation of the estimate. This distribution of this standardized variable here converges to the Gaussian normal distribution, to the standard Gaussian distribution. Yeah. So in other words, if we are in the one-dimensional setting, yeah, theta hat is again some real-valued number. We look at the probability of this theta hat n, or the cumulative distribution function, then it would resemble the cumulative distribution function of the normal distribution, with mean theta and variance being the variance of the estimate theta hat. Yeah, so here, as an illustration, we would resample more and more the normal distribution, the higher the data, the sample sizes. One important example is the maximum likelihood estimate. Yeah, so where we can make this, these assumptions are well studied, I would say. Yeah, so here we have this under specific assumptions, and for the maximum likelihood estimate, these assumptions are well studied. Yeah, so there we really have much of theory about this, and just to quickly give you an intuition what then the result is for the variance term in the multivariate case. Yeah, so we would get for the maximum likelihood estimate that it is asymptotically normal distributed, where in the variance we obtain the so-called Fisher information matrix, which is nothing else than the negative Hessian of the log likelihood. Yeah, so what we see here is nothing else than the negative log likelihood, Hessian of the log likelihood. Yeah, so here it is. Okay, so to summarize the frequentist inference tour, yeah, so the parameters are fixed, unknown constants, yeah, so some objective properties of the real world, and what we do in frequentist inference, yeah, we kind of design statistical procedures with well-defined long-run frequency properties. All right, let's come to the Bayesian inference. So we once again have our wake definition of a probability, and the Bayesians have a different point of view on this probability, on this uncertainty rather we have there. There are two ways to look at the probability in a Bayesian setting. This might be a philosophical question. I don't want to debate on that. I just mentioned that there are two ways to look at it. So the one is the subjective way, which is perhaps the most of you would agree upon. Yeah, so the probability of an event A, this would be the degree of belief of an assigner. Yeah? So therefore subjective regarding the occurrence of this event A. Yeah, so there are also some examples. So the quite well-known Dutch book argument is giving good reasons to have exactly this interpretation. But there are also other ways to look at it, also in an objective way by Cox in the 40s. Here, the probability of an event A can be interpreted as the expectation for the occurrence of the event A for anyone with the same knowledge. Yeah? So we have a specific state of current knowledge. Yeah? And because we here condition on anyone with the same knowledge, this is then more a subjective way. But either way looking, so to summarize the Bayesian interpretation would be the probability is nothing else than a belief, might be subjective or objective, about the occurrences in the real world. And the Bayesian modeling is, of course, sharing the modeling as in the frequentist. Yeah? So as I said, these two things they have in common. So we have the data and the statistical model, both relevant for that. And in addition, in Bayesian modeling, we assume a prior distribution on the parameter space theta, which we denote by pi, which is representing the prior belief of about our parameters. And what we do then is constructing a posterior distribution in the following way. So we observe data and update the belief about the parameters, so the previous belief, by using Bayes' rule. And this Bayes' rule here is, most of you know it, nothing else than likelihood times prior, more or less, plus a normalization. And to have a concrete example about the Bayesian modeling approach, let's consider the case of a three-sided dice. So there are three-sided dice available, as you see. We all know the six-sided dice, but there are also three-sided ones. And the question might be, well, what are the probabilities? So I'm quite skeptical that all faces are equally probable. So we can check this via Bayesian modeling. So what would be the data? Obviously, the outcomes of rolling the dice. And the statistical model we would use is simply the distributions p theta, where we would have as a parameter space all possible probabilities for three categories. So we see it here, this green triangle. So all points on the triangle, which is the 2 simplex, all of them are corresponding to probability vectors as they sum up to 1 and are all non-negative and at most 1. And so we will denote this by delta 3, also relevant for later on. And what would be a suitable prior distribution? Yeah, a prior distribution in this case is one where the posterior distribution stays the same in the same family. And for the Dirichlet distribution, this is the case. Yeah, looks like this. So the Dirichlet distribution puts a distribution over this parameter space, yeah, which is a simplex, probably simplex. So we see here, if we would initialize the Dirichlet distribution with all ones for the alpha parameters, and these alpha parameters are kind of representing the strength of one category, yeah, so how much the category is showing up. And here in the all one case, we simply get a uniform distribution. Yeah, could be a reasonable prior because we don't really know what this three-sided dice is about, so we put probability distribution being equal for every of the parameters. We could also have already some belief. Yeah, well, I believe stronger that all the categories are equally probable, so make all the alphas higher. And then, as I said, using the Dirichlet distribution, we stay in the Dirichlet distribution class with the posterior distribution, where we have a quite nice update formula for the alpha parameters, where we simply add to the prior alphas the number of observations of the corresponding category. Yeah, so might look then as follows, so that we have here, when we started with the all one vector, yeah, so we saw 1 time the second category and 2 times the third category. Yeah, and here it's a bit small, but it's going on, and after 49 times 3 throws, yeah, we could have the outcome that we have seen 49 times the same, all of each category the same time, and then you will see the belief about the parameter will focus on here on the fair distribution, yeah, so that really each side of the dice has equal probability. Okay, in Bayesian inference, we also have this notion of a point estimate, where we make use of the posterior distribution. Yeah, so the posterior means simply looks at the mean of the posterior distribution, as the name suggests, and then this is taken as a good guess for the parameter of interest. You can also have the posterior mode, simply the theta which is having the highest probability under the posterior distribution, or also the median might be relevant point estimate. We can also define credible regions, yeah, so similar but still different to confidence regions. So where we specify the C inside our parameter space such that the probability that the theta is inside this subset C is 1 minus alpha. Yeah? So we can also relax this to at least 1 minus alpha. The difference here is, again, in the interpretation from frequentist and Bayesian statistics. Yeah? So in the credible region, the region here is fixed, yeah? But the parameter is random. Yeah? This is how we view it in a Bayesian point of view. Confidence region, other way around. Confidence region is fixed, parameter. Confidence region is random, parameter is fixed. Okay, and then to summarize the Bayesian inference would be that all of the Bayesian statistical inference is revolving around the posterior distribution, yeah, where we saw point estimation, credible region in the same way, and these are used to making inference about the parameter. Yeah. All right, so once again, the two distinguishment between the two settings, frequentist and Bayesian, parameter fixed, statistical procedures with this long run interpretation, Bayesian inference, the parameters are fixed. We can make probability statements about that due to our posterior distribution. And yeah, this is all we do in Bayesian statistics. All right, with this, I would hand over to Willem, for the second or third part, rather.